The world's weather looks chaotic on the surface. One moment, a silent morning sky. The next, thunderstorms towering higher than mountains. A gentle breeze here, a hurricane across an ocean. But beneath this apparent randomness lies a hidden network, an intricate global system where every gust, cloud, and current belongs to a larger pattern. A system so deeply connected that a small change in one place can influence what happens thousands of kilometers away. What if weather is not disorder at all? What if it is a pattern waiting to be understood? Welcome to Mattermosaic, piecing together the universe, one discovery at a time. Today, we are exploring the hidden network of weather systems and uncovering how the Earth transforms sunlight, oceans, air, and rotation into the complex choreography we experience as weather. Every weather story begins with a mystery. Why does one storm explode into a cyclone while another fades into nothing? Why do spiraling columns of rising warm air form and stretch thousands of meters upward? Why do jet streams twist and wander across the planet like vast, restless rivers of wind? In the early days of meteorology, weather seemed so unpredictable that forecasting felt almost impossible. The atmosphere was too large, too turbulent, too sensitive. But scientists began recognizing something surprising. Despite the chaos, repeating structures kept appearing. Enormous loops of motion, global patterns, and powerful drivers that linked faraway parts of the world. One of the most important patterns begins at the equator. Because the equator receives more solar energy than anywhere else on Earth, the air warms and rises. Cooler air moves in from the sides to replace it. This movement is not just a tropical breeze. It is the beginning of a massive circulation engine. As the warm air rises, it spreads outward at high altitudes, cools, then sinks again around 30 degrees north and south. These giant loops are known as Hadley cells, and they form the backbone of Earth's atmospheric circulation. They guide trade winds, shape deserts, and influence monsoons. But the Hadley cells are only one part of the network. As we move farther from the equator, more loops form. Ferrule cells and polar cells each play their own role, creating a layered atmospheric structure that stretches from the tropics to the poles. At the boundaries of these cells, narrow bands of extremely fast winds circle the globe. These are the jet streams. They do not simply flow from west to east. They bend, stretch, break, and reform, shaping storm paths, heat waves, and cold spells. A slight shift in a jet stream's position can change the weather for millions of people. The oceans add another crucial layer to this global network. Covering more than 70% of Earth's surface, the oceans store vast amounts of heat. This drives the global ocean conveyor belt, a system of slow-moving currents that carry warm water from the equator toward the poles, while cold, dense water sinks and flows back toward the equator. This cycle takes centuries to complete, yet its influence unfolds year after year. One of the most dramatic examples is the El Niño Southern Oscillation. Every few years, warm water accumulates in the eastern Pacific, disrupting wind patterns across the ocean. The consequences ripple around the world. Monsoons in Asia weaken. Regions in the Americas experience intense rains. Droughts emerge in parts of Africa. A change in sea temperature on one side of the planet affects weather on the other side. The oceans, although slow and steady, can send pulses of energy into the atmosphere that shape global patterns. Oceans also feed shorter-term but powerful phenomena. Hurricanes, for example, begin when warm ocean water evaporates and rises, carrying heat high into the atmosphere. Under the right conditions, this rising air begins to spin because of Earth's rotation. If the ocean beneath remains warm enough and the atmosphere moist enough, the system strengthens. What begins as a small cluster of storms transforms into a massive spiral engine powered by the ocean itself. Storms are not isolated events. They are constantly interacting with the larger atmospheric network. Cold fronts push into warm regions, lifting air and triggering lines of thunderstorms. Low-pressure systems rotate and pull in air from hundreds of kilometers away. When these systems interact with mountain ranges, coastlines, or jet streams, they change direction, grow stronger, or collapse entirely. Each movement reveals another piece of the hidden structure that governs weather. One of the most important discoveries about weather came from a mathematician named Edward Lorenz. In the 1960s, he used one of the earliest computers to simulate atmospheric behavior. During an experiment, he rounded a number by a tiny amount and ran the same simulation again. The result was completely different. His discovery became known as the butterfly effect, the idea that small changes can lead to vastly different outcomes. Weather patterns may follow rules, but they are extremely sensitive. A slight shift in temperature, pressure, or humidity can alter the future significantly. This sensitivity is why forecasting remains challenging. Meteorologists gather data from satellites, weather balloons, radar, ocean buoys, and countless sensors. They feed this information into sophisticated models that simulate the atmosphere. These models generate many different possible futures. Forecasters compare these outcomes to determine the most likely scenario. Even with all this technology, predictions become less certain over time. A 2-day forecast is highly accurate. A 10-day forecast involves more uncertainty. A month ahead becomes more of a broad expectation than a precise prediction. Weather matters far beyond the science behind it. Weather shapes agriculture, ecosystems, transportation, industry, and daily life. Heat waves place stress on communities. Storm surges reshape coastlines. Rainfall patterns determine where crops can grow. As the climate warms, the hidden network of weather systems begins to shift. Jet streams drift or stall. Ocean temperatures rise, influencing storm strength. Snowpacks melt earlier, changing the flow of rivers. The network still exists, but its rhythms are changing. Understanding the hidden network of weather systems reveals something powerful. It allows us to see Earth not as a collection of disconnected events, but as a single, unified system. Every cloud, storm, and breeze is part of a larger flow of energy. Every measurement helps decode another piece of this vast pattern. Weather shows us that the planet is alive with motion. Order emerges from chaos. Global structures arise from countless local interactions. The atmosphere and oceans communicate through temperature, wind, and pressure, forming a complex story of balance and imbalance, tension and release, motion and transformation. The hidden network of weather systems also reflects something deeper about us. Our actions ripple outward, just like changes in the atmosphere. Small choices accumulate. Local effects become global shifts. When we learn to see patterns, we begin to understand both the world around us and our place within it. This is Mattermosaic, piecing together the universe, one discovery at a time. If this story ignited your curiosity, leave a like. Share it with another science enthusiast. And let us know where you want the journey to go next. Subscribe for more weekly dives into the nature of reality.